Hello everyone. In this video, I wanted to make a brief introduction into how you can perform a finite element analysis using MATLAB. So the first step is that, you need to install MATLAB in your computers. And you need to go here to Home once you have opened MATLAB. And you need to search for this option that is called Add-ons. So you click in this element. And after you click in add-ons, the following window will appear. And in this window, you can search for the toolbox that we need in order to install the toolbox that we need for performing a finite element analysis simulation. So in this search bar, you can search for many of the toolboxes that are available in MATLAB. In particular, we need the partial differential equation toolbox. Okay, that is this one, partial differential equation toolbox. You click on this part, and we need to wait until the page of the toolbox is loaded. And in this region, a button will appear that will allow you to install the toolbox in your computer. Since I already installed the toolbox in my computer, here appears a green label that says install. Okay, that means that the toolbox is already installed in my computer. Okay, and when you install any of the toolboxes that are available in MATLAB, MATLAB will be restarted automatically. Okay, in order to install all the dependencies correctly. Okay, so I will be closing this window for now. And now I want to explain what are the functions and what are the steps that you need to consider in order to apply the finite element analysis to any geometry that you already created, for instance, using a CAD software like SolidWorks or NX. Okay, in particular, we need to import this geometry um, into an STL file. Okay, so the first step, or in this case, I will be assuming that you already have um, a geometry in a STL format, okay? And this STL format can be generated with any 3D software modeling software such as SolidWorks or Fusion 360 or NX, okay? In particular, for this example, I will share with you the following STL file that is called bracket with hole. And also, you can see here that in MATLAB we have the following window that is called current folder. Okay, so you search for the current folder window, and you can notice that I have here three files. I have the example file, the bracket with hole STL file, and also I have a text document in which I have saved some of the material properties of some materials such as aluminum um, or titanium, for example. Okay, so in order to define this path, you need to define the same path in which you have already saved your STL file. So to define that, you need to click on this icon that is named Browse for Folder, and you need to search along your folders or the folders of your computer, the path or the folder in which you have already saved the STL file. Okay. So in this case, I already saved all the files that I needed in the next folder that is called string bracket demo. Okay. So I select this folder. Okay. And I can access now all the files that are in this folder, and I can access them all through MATLAB. Okay. So you can notice that in this section I have the bracket with whole STL file, and now I need to import that. Okay. And I need to define this geometry as a finite element model. Okay. In order to apply all the strain analysis, the stress analysis into this geometry in particular. So the first step is that we need to generate a finite element model based on the geometry that we want to analyze. So for that purpose, we have the following function that is called phi model. And this function requires two main parameters. You need to define the type of finite element analysis that you want to perform. In this case, I want to perform an structural static analysis. So you need to define that information with this argument. And also you need to define the geometry. And to define the geometry, we need to write the name of the geometry with the same name and extension in which it has been already saved in your folders, in your computer's folder. Okay? So in this case, you can observe that I have this, that if I define geometry equal to the name of the geometry that I want to analyze, that in this case is the bracket with hole .stl. Okay, that is the file in which I have saved the geometry that I will be analyzing in this example. And this needs to be saved in a variable that in this case I decided to label it as model. Okay, so basically what we are doing with this block of code is to generate a finite element analysis model based on the geometry that we already saved and saving that into this variable. Okay, so in order to execute this line of code or this block of code, you can press in your keyboard the following keys that are Control and Enter. And in this way we can execute this block of code. Okay. And you will notice that in the window related to the workspace here in MATLAB, we have generated the model. Okay. And you can access the properties of this model. In particular, we call this a MATLAB object. So we can double click on this element and the following window will appear. And here you can observe all the properties that this finite element model has. For example, we have properties related to the analysis type, to the geometry, to the material properties. These three properties are related to the boundary conditions associated with the faces of the geometry, the edges of the geometry, and also the vertices of the model, okay? And also, well, another important factor that we also want to modify are the loads that are applied to the faces of the geometry or the edges of the geometry. And you can define all those properties. Okay, the definition of all these properties mainly depend on the type of simulation that you want to perform, okay? So you need to define all those properties by yourself. In this example, I will be performing the most basic structural analysis that we can perform using these toolboxes. Okay, but you can specify these other parameters. Okay, just take that into account. But for this example, I will try to perform a very basic simulation. Okay, and also a very general simulation. So I will be closing this for now. And the next step is that, well, we want to visualize the geometry that we have already imported. So for that purpose, we can run the following block of code. And in particular, I want that you pay attention to the following function that is called PDE gplot. Okay, this function will allow us to visualize and also assign labels to each of the faces of the geometry. So for example, this function requires two arguments. We need to write the name of the model or the name of the finite element model that we previously created. And also we need to define this option that is called face labels. And we set this equal to on. Okay. And this instruction will allow MATLAB to not only plot the geometry that we have already imported, but also we can visualize or assign labels to each of the faces. And based on that labels, we can define boundary conditions and also specify in which phases we will be applying certain loads. Okay. So if you press again Control Enter, the following window will appear. Here you can observe that we have already imported the geometry. This is like an isometric view of the geometry. And one of the important aspects that I want you to notice is that, well, this is the coordinate or the reference coordinate that we are using in order to visualize this geometry. In this case, this is the direction of the x-axis, this is the direction of the y-axis, and this is the direction of the z-axis. The identification of this reference frame is important because based on this reference, we'll be applying the loads to each of the faces of the geometry. Okay? Also, you can observe that for each of the faces of this geometry, MATLAB has automatically assigned labels. In total, the labels are assigned via numbers. So you can observe we have a total of 13 labels that are related to the number of faces in the geometry. And also this is helpful because we can observe or we can define based on these labels which faces will be used as boundary conditions and in which faces we'll be applying certain loads. Okay. So for this geometry, we will be using the back face of this geometry, that is face number 4, as a boundary conditions. In this case, we will be assuming that this face is fixed. And also, we will be applying a load to face number 8, that is the front face of this geometry. Okay, and in particular, we will be applying the load pointing to the negative z direction. Okay, so this load will be applied to face number 8, that is this one, and I will establish that this load will be applied to the negative direction of the z-axis. Okay, and we want to analyze what is the displacement along the z-axis when we apply a certain load value into this face, by also considering that the back face of this geometry is constrained or is fixed. Okay, so I will be closing this window for now. We can continue. So the other important step that we need to define is what are the material properties of our geometry. Okay, so to do that, we need to modify the material properties of the model that we have already created. Okay, so to do that, we need to first access to the properties of the model, in particular the material properties. In this case, well, you need to write model, then you need to write a dot in order to access the properties of the model that we previously visualized, okay, by double clicking here in the workspace. Okay, these are the properties or all of the properties of the model, but in particular, we want to modify the material properties. And well, this should be equal to material properties. That is the function that will allow us to modify the material properties of the geometry. And in this case, and only as an example, I only defining the Young modulus. This is an arbitrary value. And also you need to define the Poisson ratio, okay? But remember that these material properties will depend on the material that you will be defining for your geometry, okay? So this aspect depends mainly on your decisions, okay, as a designer. So that is one important factor. And also, I wanted to mention that the units in which you need to express, for example, the Young modulus should be expressed in international units. Okay, so in this case, I am assuming that this value is in pascals. Okay, so you need to be very careful about that because MATLAB will assume that all the operations will be performed by considering international units. Okay. So we can now execute this block of code by pressing the Ctrl and Enter keys in your keyboard. And well, if you want to verify that these properties have been changed, you can double click here in the model, and then you need to go here to material properties. Okay, And you will notice that, well, the Poisson ratio and the Young modulus have been changed, or now they have a value. That is the same value that I already assigned in this part of the code. Okay. So after that, we can now define the boundary conditions of the geometry. So to define the boundary conditions, again, we need to write the name of the model. We need to write a dot in order to access to the properties of this model. And in particular, we want to change the properties related to the phase boundary conditions. And also you can notice that under parentheses, I write the number or the label in which I want to apply a boundary condition. Remember that we mentioned previously that I want to set as a boundary condition the phase number 4. Okay, that is why I am placing under parentheses the number 4. And this should be equal to the following function, that is phase BC. This function will allow us to modify the boundary conditions of any phase in our geometry. And in this case, I want to tell MATLAB that I want that this phase is fixed. Okay, that is why I am defining as a constraint. Well, I am defining this constraint, okay, equal to fixed. So now you can again execute this line of code by pressing Ctrl Enter. And then you can go here to model, you double click on that. And well, remember that we modify the boundary conditions of the faces. And here you can see that we have the following cells, our matrix in which we have the different columns. And each column represents the different faces that we have in our geometry. And in particular, if you want to access the properties, for example, for phase number 4, that is the one that we modified, you need to double click on this cell. And you can observe that, well, we have defined the constraint for this phase boundary condition as fixed. Okay, you can also define other boundary conditions, but in order to maintain this simulation as simple as possible, I only decided to set the property constraint. Okay, so I will be closing these windows for now. And the following step is to define the loads that will be applied to the faces of the geometry. So as I mentioned before, I wanted to apply a particular load pointing into the negative z direction, okay? And remember that the phase in which I will be applying this load is phase number 8. So to specify this aspect in our model, you need to write the following code. First, you need to write the model, that is the name of the finite element model that I defined from the beginning. Then you need to write a dot, and then you need to write the property that you want to modify from this model, that in this case is the phase load. And under parentheses, I am specifying to MATLAB that I want to change the properties related to the loads for phase number 8. Okay, that's why I have under parentheses this number. And this should be equal to the function phase load. This function will allow us to change the properties related to the loads applied to the faces of the geometry. And in this case, well, we need to set as an argument the parameter related to surface traction in order to specify the components of the load that will be applied. In this case, the components of the load needs to be specified in its x and y and z directions. Okay, so for example, here we have a vector in which the first element of this vector is the magnitude and direction of the load applied to the x-axis. This is for the y-axis, and this is for the z-axis. Here you can observe that I write a negative sign in order to specify to MATLAB that in the case of the z-axis load, I want that this axis is pointing to the negative z direction. Okay? So you can specify the direction in which the load is applied by placing a negative or positive sign. And also, you need to specify the magnitude. That in this case, based on the MATLAB notation, this load is equal to 1 times 10 elevated to the 4 power. Okay? And remember that this magnitude should be expressed in international units. That is, we need to specify the load in newtons over square meters. Okay? And well, that is uh, all the aspects related to applying a particular load to a face, okay, of the geometry. So I will erase all of these things. And now, well, just a moment. The final step before performing the finite element analysis simulation is to generate a mesh. Okay. So, well, in order to generate a mesh for our geometry, well, we can use the following function that is called generate mesh. And you need to write under parentheses the name of your model. And well, in this case, I am modifying the same object. Okay. So I am making model equal to generate mesh in order to generate the mesh and save that mesh into the properties of our model. Okay. So, and well, this line of code basically will plot for us the mesh that has been generated for our geometry. So if you press Control Enter in this block of code, the following plot will be generated that basically represents the mesh that has already been generated for our geometry. Okay, so this is the mesh, and well, now we can solve um, the the model based on the mesh that we have already defined, and also based on the boundary conditions, the material properties, and the loads that we have previously defined. So to solve the finite element model, you need to use the following function that is called solve, and you place under parentheses the name of your model. And in this case, I am assigning this result to the following variable that is called result. Okay, so again, you press Control Enter, and you can observe that here in the workspace, we have now available the results related to solving this finite element model that we have previously defined. So if you want to access the results, you can double click here in this object. And here we have properties related to the different results from the structural static analysis. For example, we have information related to the displacements in the geometry, in the X, Y, and Z direction, and also the value of the magnitude of this displacement. We have also results related to the strain analysis, okay? The stress analysis, and also the von Mises stress, okay? So, well, now we can press Control Enter right here. Well, I think that I was missing something. Being that I didn't execute the code related to the load, that's why I'm showing here a 0, because I didn't specify or define the load correctly. So I will be running this code again. And well, I will execute this code again. And you can observe that again, the mesh has been generated again. And now we can execute the solution of our model. And well, in this line of code, basically what I am doing is to compute what is the maximum displacement along the Z-axis. So again, you can Control Enter this block of code. And here, well, let me erase my command window. I will press again Control Enter. And here you can observe that we have here the maximum deflection, no? Along the Z direction by, well, setting the material properties, the boundary condition, and also the loads of the geometry that we are analyzing, okay? So according to the finite element analysis simulation, we have this displacement of minus 4.46 times 10 elevated to the minus 5. Okay. Also, we can plot graphically what is the displacement in our geometry according to the parameters that we previously defined for the x, the y, and the z axis. So for that purpose, we need to use the following function that is called PDE plot 3D. And this function will allow us to show graphically what is the displacement in our geometry along the x-axis. And well, when using this function, well, we have to define two parameters. First, we need to have or introduce the results of our model related to the mesh that we created. And also we need to, well, we can define a color map for our results when plotting it, the displacement along the different axes of the geometry. And we want to generate a color map that is equal to the results displacement along the x-axis. So to do that, you need to write results, then you need to write a dot, and then you write the word displacement, and then you write again a dot. And in this case, we are telling MATLAB that we want to generate a color map based on the x-axis displacement. So you click again, Control Enter. And well, here we have like the results related to the displacement along the x-axis for our geometry and based on the boundary conditions and also based on the load that we applied. We can generate a similar plot for the y-axis using the following code. Okay. And well, here you can see that in the color map, we are showing what is the displacement also. Okay, according to the finite element analysis results. Well, remember that in this case, we are interested in the z displacement, okay, or the displacement along the z-axis. So, well, in this case, here I am showing you how you can plot these displacements along the z-axis and also visualize these displacements graphically. So again, you press Control Enter, and here you can observe that in phase number 4 that we define that this phase will be constrained. There is no displacement according to this color map. But you can observe that these regions have a greater displacement, okay? And as we move in this direction, you will notice that, well, there is a greater displacement as we approximate to phase number 8, okay? That remember that this is the phase that was in this region, okay? In particular, this one, okay? That is the front face of the geometry. So this is a way in which you can visualize graphically what is the displacement according to the loads and the boundary conditions that you previously defined. And also, well, this displacement will change depending also on the material properties that you define for your geometry. Well, another type of plot that you can generate is visualize the von Mises stress, okay? That is, well, to which your geometry is subjected. So again, we can use the PDE plot 3D function, and then the first argument is related to the results of the mesh that we previously generated. And also we want to define a color map based on the von Mises stress results, okay? So again, if you want to access the results related to the von Mises stress, you need to make this parameter named color map equal to the result dot von Mises stress in order to define this color map based on these results, no, of the von Mises stress analysis. So again, we press in your keyboard Control and Enter. And here we can observe the von Mises stress results. Here are the magnitude of this stress. And remember that, well, Based on this color, we can see which regions of the geometry are experiencing a greater stress compared to the other ones. In this case, based on this color map, we can see that the regions that have a greater stress are these ones, okay, and also this region. Okay, also remember that this stress is mainly dependent on the geometry and also the boundary conditions and loads that are applied to the geometry. Okay, so this is like a very general example in how you can perform this type of finite element analysis using MATLAB. Okay, it's a general overview of how you can do it. Also, I will share with you the code and also the geometry in order that you can run this code in your computers and have the opportunity to analyze um, the sorry the results by yourselves, and also that you have the opportunity to get in touch with all the functions that are available here in MATLAB. And also, I recommend that you explore all the properties that you can define from your model. There are many parameters that you can set, okay? So depending on the type of analysis that you want to perform, you can make this finite analysis more complex, okay? But that is an aspect that you need to define or that you need to discuss with your team in order to see how you can use this tool and adapt this tool to your project related to the flange that you need to design for Generac. Okay, so I will share this code and also this well, all the files that you need in Canvas. And if you have a question or doubt, well, we can discuss this during class. Okay, so that's all for me, and see you later.